So yeah, the next speaker is actually Sreenath, but we call him Sri here. He will talk about the statistical arrow of time and some thermodynamics and some clocks and all the things you work.
Yeah, thanks, Vasilis, and also to all organizers. So I'm going to talk about, so the title here looks slightly different, but basically thermodynamics of quantum measurements and then interesting applications to clocks and also engines and refrigerators. I'll also talk about arrow of time for quantum measurements in this talk. So here is a brief overview of topics I work on. I am interested in different scales of quantum systems. In the small quantum systems regime, it's quite interesting because you can use simple qubits and quantum oscillators and continuous measurements to probe different symmetries related to time, for example, time reversal symmetry and time translation symmetry. And in the mesoscopic systems regime, this is where many body quantum effects come into play. You can also have quantum advantages or advantages, especially when it comes to thermodynamics or applications to cooling in the quantum regime. And then also large quantum systems is also interesting test beds for analog gravity of quantum analog analogies to quantum proposed quantum theories of gravity in tabletop experiments, as well as tests of low energy signatures for quantum gravity. So in today's talk, I will focus on the first part mostly, and I'll give a brief introduction. I will talk about arrow of time for quantum measurement process and also fluctuation theorems which constrain this arrow of time from a thermodynamic viewpoint. And then I will talk about quickly cover three applications of this, which include engines, refrigerators, and clocks. So as you know, equilibrium thermodynamics is classical thermodynamics. It was largely motivated by the need to optimize engines and refrigerators. So for example, you can have different thermal reservoirs coupled, and you can make use of a temperature gradient to get some work out of the system, and you can characterize the performance of that device with an efficiency. And there are also refrigerators where you do some work to cool down one reservoir relative to another, and then you can have figures of merit like a coefficient of performance. There are also some recent works on thinking that clocks are also thermodynamic systems. Here are some nice references. The idea is that the heart of a clock is an engine which does the necessary work to fuel the ticks of a clock, and therefore the precision and accuracy of the clock should also be limited by thermodynamic principles. I would largely skip most of the recent developments in this field, and I will go into the quantum regime of thermodynamics of small systems. By small systems, what I mean is that the energy exchanges in the system are of the order of a few kBt, and also the ensemble size that we are describing are small. So we have like 10 or thousands of qubits, or even more single realizations of processes happening at the level of a single qubit. And this is an interesting regime of physics to explore, because fire, as you know, it's one of the oldest inventions of mankind, and these delicate quantum technology platforms are kind of the newest. So we are putting them together, and interesting things are expected to emerge out of this discipline. So so the time reversal symmetry, essentially it's better called the reversal of motion symmetry. So the way to understand this is that if I record a movie of throwing a ball up in the air and play this movie backward, I would not be able to tell by simply watching the movie alone which direction this movie was recorded. And it is evident from this symmetry is evident from the dynamical equations which describe the system. In this limit, the Hamilton's equations of motion, they are time reversal symmetric if I put t going to minus t and p going to minus p in these equations. Similarly, in quantum mechanics, the governing dynamical equation is the Schrodinger equation, and it is also time reversal symmetric if I put t going to minus t and also complex conjugate across the equation. And the observables also change under time reversal in correspondence with their classical counterparts. However, there is this process which is quantum measurement, which seems to break this time reversal symmetry in the strongest sense, in the sense that in textbooks we describe a quantum measurement process as a black box, which is the measurement apparatus interacting with the system of interest. it gives us real numbers as outputs. These are the eigenvalues, and then corresponding to each of these real numbers, we update our knowledge about the quantum system by applying a projector on the initial state of the system. And this projector can have zero eigenvalues, and as a matrix, this is not reversible. So there seems to be some sense of irreversibility in the way we acquire information from a quantum system. We can, so the way we kind of try to get around this issue is by considering continuous weak quantum measurements. If you have questions in between, please do stop me. So let's think about measuring a single qubit. And the idea is that the qubit is initially prepared in some arbitrary superposition state, and we want to measure the spin of the qubit. The idea is to couple this qubit to the spin degree of freedom to, let's say, momentum of a wave packet. So what is interesting about coupling to the momentum degree of freedom of a wave packet, this could be an electron or a photon wave packet, is that now the wave packet undergoes displacements conditioned on the spin state of the qubit, because momentum generates translations in the Hilbert space of the wave packet. And then we can look at do a quadrature measurement, measure a quadrature which is complementary to momentum, let's say position of the wave packet, and we get a weak information about the spin state of the qubit that we wanted to probe. And these measurement operators have this Gaussian form because we assume a Gaussian wave packet to start with, and they also satisfies the completeness relation. And one can have a sequence of these realizations. Basically, another photon now comes by and interacts with this system of interest, and we do a quadrature measurement of the second photon, and the third photon comes and we interacts with the system, and then we measure the quadrature of that. So we can get a quantum trajectory, which is a sequence of these states conditioned on the readout that you get at each instant in time. And one can also associate the path probability density that a given trajectory is realized. This I would call the forward probability. And just to contrast this with the conventional picture of strong measurements, the idea is that one could make an analogy to butterflies leaving a nest and going towards two different trees. In the strong measurement limit, you only get the information about which of the two trees the butterflies eventually landed. But what this continuous weak measurement allow us to do is that in addition to the two trees, we can also basically track the route through which the quantum state evolves to an eigenstate. This also introduces the possibility that one can have reversibility at each step, because these measurement operators are Gaussian. We can have the possibility that in the next step, the readout can have the opposite sign of the previous readout, and therefore these two measurements can they cancel the effect of each other. So one can in principle statistically go back a step in this continuous measurement process, just to say that the butterfly can fly a little back towards the nest with some probability of success. So what this means is that if I make a movie of the qubit state dynamics in the Bloch sphere, I can record this movie, play it forward and backward. Just by watching the movie alone, I would not be able to tell which direction this movie was originally recorded. And it is also evident from the dynamical equations which describe the qubit state subject to continuous measurements. So here R is like the readout variable that you get through from these continuous measurements. So these equations are time reversal symmetric. Basically, if we put t going to minus t and then flip the Bloch sphere coordinates and also flip the Hamiltonian here because you have a spin, so the magnetic field changes sign under time reversal, and then also put r going to minus r, which is the symmetry I was describing, these equations retain the same form. So just by watching the movie, I would not be able to tell which direction the movie is recorded. And in fact, this principle also applies to arbitrary rank 2 weak quantum measurements on a qubit. So what we can do is that we can leverage on the access to the measurement record. If we assume that we do not have any prior information regarding which direction the movie was recorded, I can use this measurement record as a soundtrack for the movie to update our knowledge about which direction this movie is recorded. And this gives us a natural discriminator, which is the logarithmic ratio of forward and backward probabilities as a measure, which we will call the arrow of time. Now this is a trajectory dependent quantity. If I repeat the measurement, another realization of the measurement will have a different statistical arrow of time. So I can make probability distribution of this arrow of time, and I can do this for different kind of measurements. For example, the first one is a fluorescence measurement. An atom is emitting a photon, and we measure one quadrature of the photon. This is a homodyne detection of fluorescence. There could also be scenarios where an atom is emitting a photon, and we measure both quadratures of the photon simultaneously. This would implement a heterodyne detection of fluorescence and the spin measurement that I was describing. So all these processes, we can make probability distributions of this arrow of time. And what you see immediately is that the average of the arrow of time is positive. But then also these distributions are not Gaussian. So the first and second moments alone do not completely characterize the system. So we need to look into relations that constrain the entire probability distribution to acquire all the information encoded in these distributions. And here we use what is known as fluctuation theorems for small classical systems. The idea is that for small classical systems, entropy can be a fluctuating random variable, and thermal fluctuation can assist entropy processes where you don't need to do as much work as compared to the free energy difference to complete the process. Sometimes the thermal fluctuation can assist you in completing a process, sometimes it can resist completion of a process. But on an average, the entropy is always greater than or equal to 0. And in these cases, what one computes is the average of exponentiated entropy production. So this will be something that looks at all the higher order moments of the probability distribution, and there has been fluctuation theorems derived for small classical systems which says that this has to be equal to 1 or number between 0 and 1. So with this motivation, which I skipped a little through, we look at the exponentiated average of exponentiated arrow of time, and we get a number between 0 and 1. And these kind of processes are also known in classical thermodynamics of small systems. These are absolutely irreversible processes. An example is free expansion of a single gas particle in a box. So if I have a process where a molecule is constrained on the left hand side of a box, I can remove the partition, and the particle will expand to both sides. It could be found on the left or the right. The backward process would be where I reinsert this partition, and there is only one path that basically you go back to the initial conditions. Because you expand the phase space volume in the forward process, it generates more possibilities, and therefore there is an absolute irreversibility. So if I compute the entropy, everything can be done with equilibrium thermodynamics considerations, compute the free energy for a particle in a box and so on. We find that the average of exponentiated entropy production is between 0 and 1. What this means is that exponential function is a convex function. So then the average of the arrow of time, when you compute, you get a number which is greater than a positive number, as opposed to the scenario where average of arrow of time or entropy is greater than or equal to 0, which is the usual statement of second law of thermodynamics. This is a stronger version of the second law of thermodynamics, which is called absolute irreversibility in classical systems. And in this scenario, what this degree of absolute irreversibility parameter that comes on the right hand side of the fluctuation theorem means is that it computes the degree by which two initially orthogonal states are taken closer and closer as a result of the quantum measurement. As you know, a measurement process can be a many to one mapping process. So this degree of absolute irreversibility in the quantum measurement problem reflects the many to one mapping aspect of the quantum measurement, and it constrains this arrow of time that I was talking about using fluctuation theorems puts it in a more thermodynamic framework. And we had looked at some experiments. So the simplest experiments one can think about is Stern-Gerlach type of spin measurement. So you prepare atoms in a given initial spin state and then put them through a magnetic field gradient. And in this case, the position of atoms would reveal weak information about the spin state of the atom, just like the initial distributions that I was showing. And for this case, we can characterize different aspects of the fluctuation theorem by simply looking at the picture that one makes in the end of this experiment, the cloud absorption image. We have also looked at this framework for initially correlated atomic clouds. So we take a Gaussian cloud and then a spherical cloud and then attach different modes of this into different spin degrees of freedom. And one can also extend this fluctuation theorem to compute the absolute irreversibility of quantum measurement in these kind of scenarios. And now I'll come to the final part of my talk. I want to talk about 3 examples where this is useful in the thermodynamic sense. The first one is a feedback controlled engine. The idea is that we have a qubit and we measure the spin state of this along the sigma x axis. So now the measurement kicks it to a higher energy state, which could be either plus or minus eigenstate of or close towards these eigenstates. But then I can extract work from this by applying a feedback which rotates the qubit state back towards the ground state. And then the question is that if the daemon is doing a weak quantum, the experimentalist who is doing this weak measurement is a Maxwell's daemon. The daemon can basically play the game of recording this measurement process and playing it forward and backward, associate an arrow of time for the process. And the interesting question is, how does the arrow of time perceived by the Maxwell's daemon relate to the work that the daemon can extract from the system? And we find that one can in principle write down the work that a daemon can extract in these kind of scenarios is completely determined by the arrow of time, statistical arrow of time that the daemon infers for individual realizations of the measurement process. That's what's shown here. And the other example I want to highlight is the idea of quantum clocks. So the clocks are interesting systems because a perfect clock would break time translational symmetry. And the interesting question here is what are the ways you can get a clock signal out of a system by only consuming thermodynamic resources. So you should not have another clock in the dynamical description of a clock, new clock. So we look at scenarios where we pump the excitations through an irreversible channel, which is a measurement, which can be thought of as a measurement process. So if you have a system continuously under measurement, but then this measurement apparatus is broken in some sense. So the measurement is happening, we are not acquiring any information. So there is no way to undo these effects of measurement, even for weak measurements. And we find that and then monitor the ticks that come out of this two-level system through resonant fluorescence measurements. And what is interesting is that the finite time statistics of ticks coming out of this two-level system can be solved using large deviation principle, and we can characterize the quantum nature of these clock ticks and what is the effect of somebody watching the clock tick on the ticking rate of the clock itself. And that is captured by this Mandel's Q parameter. When it is negative, it means that these are sub-Poissonian, they obey sub-Poissonian statistics, which means that the clocks tick more regularly than a Poissonian clock. And one uses a tilted-Lindblad approach to compute the large deviation calculations here. Finally, this is work with Sophia. I would like to highlight one cooling applications of continuous measurement. So one possibility is that if you are familiar with the child in a swing problem, if a child is oscillating in a swing and the child decides to stand up and sit down at twice the frequency of the natural frequency of oscillation of the swing, the child can increase or decrease the amplitude of the swing. And whether you increase or decrease depends on where in the cycle the child decides to stand up and sit down. So the same principle can be applied to quantum systems too. But then the interesting thing is that we need to acquire the phase information of a quantum oscillator, and this requires measuring both quadratures of an oscillator simultaneously. And this introduces fundamental noise limits into the oscillator. So what we find is that we can cool down to below 1 quantum, which would qualify as a good method to reach ground state, because then one can combine it with linear feedback cooling techniques. But there is a fundamental limit which comes from the noise added by the quantum measurements of simultaneous measurement of joint non-commuting observables. With that, I will conclude. It is interesting to think about quantum measurements as a new paradigm where one can think about irreversibility, which can be rectified to produce some useful work or produce ticks of a clock or so on. So there is interesting thermodynamic aspects to this. It also attempts to address interesting questions in relation to the symmetries of time using simple quantum systems, which can be accessed in experiments. For example, in this work, it's using superconducting qubits or ultra cold atoms. With that, I will conclude. Thanks.